Welcome back to another statics video. We're in chapter 5 in the textbook looking at frame analysis. So we've already done one frame analysis example, and so I'm going to run through a couple more examples here to help you out, including one of the homework problems, 518. So first thing we want to do when starting a frame analysis is to find the reaction forces, and we also need to find any missing geometry. Now, when we did truss analysis, finding missing geometry was all about finding angles, but for frame analysis, we're actually a little bit more concerned about distances because we are going to potentially have moments that we need to solve for. So for instance, in this problem, one of the pieces of geometry that we're missing is this vertical distance from A to D. We're going to need to know what that is, and it's not given to us, at least not directly, but we can find it based on the information that we do have. Okay, and that information would include the fact that this distance here is 8 feet long, the distance from D to B, and we are given this angle here of 40 degrees. So we basically have a right triangle that is 40 degrees, and we know this side of it is 8. So we need to find that side. Okay, so if we're looking at this 40-degree angle, the unknown side that we want to find is the opposite side. Opposite. So, and this side is the adjacent side. So we want to know opposite. We do know adjacent. TOA, tangent. So we're going to use tangent to find it. Tangent of 40 degrees equals the unknown opposite side. I don't know what we'd call that. We could just call that question mark, I guess. Over the adjacent side is 8. Okay, so our unknown side is going to be equal to 8 times tangent of 40. So that is 6.71 feet. So we'll need to know that going forward. So we have found that. Now we can find the reaction forces. So we have just two applied loads here, 2,500 and 3,000. We know that there are going to be vertical reaction forces here at A and D that are going to resist these two, but we don't know how it's going to be shared. So what we may need to do is actually leave those two vertical reaction forces as unknowns. You can call them, I'll use the textbook author's annotation method of dV for vertical and AV for vertical, and we may not know what they are when we begin our frame analysis, and that's okay. Now in the x direction, we know that these two forces, these externally applied forces, are pulling this whole frame down, which is going to try to rip it out of the wall up here. So that means the reaction force in the horizontal direction, AH, is going to be going to the left. It's going to be pulling back against that, which therefore means that the reaction force down here at D, DH, is going to be going to the right. Those two things are going to cancel each other out. Okay, and can we find one of those? I think yes, we can. We can sum the moments about the bottom left corner about D. So AH is going to be going to the left, which means it's going to make a counterclockwise rotation, which we call positive. So we've got positive AH times 6.71. Then what else do we have? We've got 2,500 coming down, which is going to cause clockwise rotation. That's negative. So negative 2,500 times 4. That's its moment arm distance. And we've also got minus 3,000 times 12. And those three forces, those three moments, will all cancel each other out. And so if we solve that equation, AH is going to be equal to 2,500 times 4 plus 3,000 times 12, and then that all gets divided by 6.71. So AH is equal to that gives me 68.55, and if we round that off to three significant figures, that's going to be 68.60 pounds. So that's going to be 68.60, which means that DH is also going to be 68.60. And so we've got the two horizontal reaction forces. We don't have the vertical reaction forces yet, but I guess the thing I'm trying to explain is that in frame analysis, if you run into a situation like that where we don't know how to find those forces, that doesn't mean you have to stop. That doesn't mean you've hit a dead end. It just means that you need to take a different approach, look at it from a different angle, go on to a different part of the frame, and then eventually that missing piece of information will be found and we'll be able to come back to it. So this gets us started here, knowing the horizontal forces, and now we can move on to looking at one individual frame member. Okay, so I think I would probably start with the horizontal member. No particular reason there, I guess. We've got the 3,000-pound force at the end. We know that the reaction force is pushing to the right 68.60, and we've got this joint B here, and we can assume that it's going to be pulling it up to counteract the external load applied out here at the end. This diagonal brace, that's really its function, is to hold up the horizontal member. And then we also had this vertical reaction here that was unknown. dV, BV. And in the horizontal direction, since the reaction force is pushing against the horizontal member to the right, that means that BH must be pulling it back to the left. The pin, as it is affecting the horizontal member, is pulling it back to the right. And those two things are going to cancel each other out. So right off the bat, we know what this one is. This is going to be 68.60, just like the reaction force. Those are the only two horizontal forces here. So we could write it out formally. Sum of forces in the x direction equals 0, which equals 68.60 minus BH. Therefore, BH equals 68.60. Okay, or we could just look at it and recognize we've only got two horizontal forces. They must cancel each other out. This one's 68.60, therefore this one is also 68.60. Now, when it comes to finding the vertical forces, we can sum the moments about D. And so those are going to include BV. Those moments are going to include BV times a moment arm distance of 8. 4 plus 4 is 8. And that's going up. Up and around is counterclockwise. That's positive. And then we have the 3,000 force out here. That's going to be going down, which is going to be clockwise or negative. 3,000 times 12. And that's going to equal 0. So then we can solve for BV. BV is equal to 3,000 times 12 divided by 8. And so that equals 4,500. And if BV, B in the vertical direction, equals 4,500, now we can find DV because we can sum the forces in the y direction. We have DV, which we assume is going up. We also have BV, 4,500 going up. And we have the 3,000 pound force out here at the end. The sum of those three forces should equal 0. So if we solve for dV, watch what happens here. We've got dV equals the positive 3,000 and the negative 4,500. You get negative 1,500. So up until now, when I have been guessing at the sense of a force or reaction, I've basically been correct every time. This is the first instance where, like I said, if you guess that the reaction force here was going up and you solve for it and you actually find it's not, you get a negative answer, it's still 1,500. All that means is we weren't correct about the sense. It actually is going down 1,500 pounds. Okay, and you can think of this, again, almost like the teeter-totter I mentioned in an earlier example. This reaction at B, the pin is holding that horizontal member up. And then we've got the force out here at the right pulling it down. So we also have a negative reaction force down here at the left. So these two forces at either end are balanced about this. It's sort of like a fulcrum, a pivot point in the middle of the horizontal force. So if we know this force is going down 1,500, that's going to help us find A up here. This is definitely going to be going up now because now we've said we've got that going down, and this going down. All three of these forces are going down. So we can take a step back, look at the overall frame as a whole, and we can find the reaction force, the vertical reaction force at A, by summing forces in the y direction. That's going to equal negative 1,500, negative 2,500, and negative 3,000, plus A in the vertical direction. So that means AV is equal to 7,000 pounds. Okay, so again, this exemplifies a couple important things. One, we didn't know these vertical reactions when we started the problem. That's okay, just move on. Eventually, you are going to be able to determine what they are. And this is the first example in which the assumed direction of a reaction force was wrong. By solving it, we got a negative answer, and so that means that we need to change the direction of our assumed force. Okay, so now that we have AV and we've got the reactions at B and D, we really have all of the pin reaction forces, but we could still analyze this diagonal brace just to make sure everything does in fact cancel out. I'm going to have to do that in the next video because I'm just about out of time.